Thank you. Thank you, Noah. Unfortunately, you're going to see more of those logs now. So beware. I'd like to, in this quick presentation, probably I will repeat some of the comments already you've heard before, but for some of you it might be sort of another angle to look at what you perhaps learned before. And I'll try to point out a few areas where I believe there is room for a high-tech industry in Israel to contribute to the industry. So areas that you are, if you are working in, it might raise a flag and say, hey, you know, maybe I can add to that particular industry. Before, a few words on our company, Paradigm. We have about 700 customers, which is basically, if you think about it, probably everyone in this industry. Most of them are global customers, super majors, national companies, large independent. We founded in 1988 with the help of our Israeli chief scientist, which I met over here, which is sort of nice, with 26 years in business. About 700 employees, a bit more actually. About 115 in Israel. 61 PhDs, so as you can understand, this is very science-based business, and you need to have that brain power behind such companies. About 29 offices, 24 countries, so it's a very global business. 15,000 geoscientists are using our system and technology every day to make interpretation and data processing and geoscience decision every day, similar like you have seen in the talks before. Long-term relationship with our top customers. We sell every year more than $200 million of software licenses, and as you've heard before, we've just been acquired by Apex Partners, which is a for those of you who are not familiar with Apex, they acquired Tnuva and Bezek here for about $1 billion. A little bit about our R&D centers. We invest every year about $45 million in R&D. That R&D is very specifically focused on software development in the area of geoscience. We're about 240 professionals in many, many disciplines. So it's not just geoscientists. Obviously, we have geoscientists, data management, high-performance cluster computing, high-end graphic computing. Geoscience is just not, I mean, it's one word, but it's actually many disciplines. You talk about geophysicists, geologists, petrophysicists, rock physicists, etc. The code base we have is about over 20 million lines of code. It's a very significant system, and it's developed in 7 R&D centers in Houston, Aberdeen, Paris, Moscow, obviously Herzliya, which has been where we began, and Brisbane. A little bit of the issues of this industry, and again, I think you've heard some of it before. Cost of drilling is very high. So for those of you in the high-tech side, you're saying, well, definitely there is an opportunity because this industry has significant requirements and significant risks. So $100 million plus well is obviously, not obviously, but something that is quite common. We're dealing with a lot of data. So we talk about, 100 of, currently the total number of data that our industry has is over 150 petabytes of data. So we talk about a huge amount of data, and they need to integrate many different data types, as you already have heard. So the challenge is becoming more complex. We need to deal in more remote places, deeper locations, onshore, offshore. Unconventional oil, as you already seen before, is a very complex process to extract the oil from. And in parallel, you have obviously an increased concern for environmental safety and regulatory compliance that you need to deal with. Well, perhaps the good news here for us in the supply side, the industry is also spending a lot of money to resolve those problems. I mean, E&P spending in 2012 actually were approaching $600 billion. So it's a very significant amount. This is just the upstream part in exploration and production, $600 billion, and it's growing fast. It's a 10% increase from previous record of $544 billion in 2011. So there's a lot of money the industry is spending. A great deal of that money obviously is not just for technology, but for pipes, pumps, all the sophisticated drilling that you have seen, but it's a significant industry with a significant capital spending budget. We're looking at, and again, you've heard before, still industry is looking at increased needs to spend more money and spending. We use the high technology in order to extract more oil because we need more oil. Even with the unconventional, the various alternatives, natural gas, we still need more oil in order to sustain production and sustain the needs of the world. Out of this big $600 billion, obviously, not all of that goes into the part that I'm interested in, or perhaps some of you would be, which is the high-tech or the software, the technology side, but still a good amount. The sector that we're dealing in, which is the software and related services for geoscience, is about $3 billion a year. This is what industry is spending in our sector. And as you've seen, it's a complex process. In order to spend the entire E&P life cycle, we need to deal with exploration, appraisal, development, production. All those should be integrated into a single database and single environment. If you look at the asset life cycle, we're talking about basin development, where we develop a full basin. Then we go into more detailed prospect generation, discovery and appraisal, development production, enhanced recovery, and eventually abandonment of the field. And all of that should be also dealt with a lot of data management, data administration, which is generated throughout this big process. A life cycle of a field could be about 25 years, even more. Some of the fields that actually are in operation today in Saudi Arabia were discovered after World War II. So this is a significant and very long-term process which you keep iterating and collecting more data until you find additional resources. I mentioned about the industry being data intensive. Industry spending every year is more than $10 billion on data collecting, acquiring seismic data, well data, and many other different data types. Current archive of data, again, about 150 to 200 petabyte of data. Industry is adding every year, say, about 10 petabyte of new data. So we need to deal with a lot of data, and a lot of data that comes very quickly. Now we need to deal with many different data types. That's part of the challenge. It's not just seismic, it's not just well data. Even well data is not just one type. You already heard before, there's many different types of data, many different types of logs that you need to deal with. A lot of information about the well, how it's been drilled. Talking about data that is specific on for the rock. New type of information that now we have, which is digital rocks, which you actually convert the rock into a digital format and then analyze the rocks. All those different data types need to be integrated, and all of them are for different scale. So the scaling issue is one of the challenges that we need to deal with. Seismic data could be at the scale of tens of meters. So minimum resolution for seismic data will be the size of this room. Log data, the resolution is the size of a few centimeters. Then if you go into rock physics, you're talking about microns. So all of a sudden you have data with a lot of different vertical resolutions that you need to deal with and integrate into a single cohesive image of the subsurface. So a typical workflow would be, you have all your different data types. seismic data, satellite data, well data, production data, all should be integrated, crunched into and analyzed by using those massive computers that you have seen, and then the output would be 3D or 2D images of the subsurface that the interpreter, which will perhaps be the equivalent of a doctor if you wish, looking at the subsurface and making decisions. There is oil, there isn't oil, where to drill, what to do, how to produce. It's also an iterative process. I want to emphasize it's not just something you do once, but you keep doing. So you have information, seismic data, 2D, 3D. We are now using 4D, which meaning shooting the same seismic information again and again in on the same field, using massive parallel processing to process the data, analyze the data, and then display the information for the interpreter to make decisions. And you keep doing it throughout the lifecycle of the field a few times. Another thing that is sort of maybe not so obvious at the beginning, we're talking about oil and gas in general, but you need to be very, or sometimes quite workflow specific, meaning that what you design to work in one geological regime or one basin may not be the same as you need to deal with another area. So let's say if you have a lot of experience dealing with Siberia data, it doesn't mean that it's applicable to Gulf of Mexico. Or if you're dealing with the Levant Basin, it may not be the same as you're dealing in China. So we have different different geological problems. So for each one of them, we need to design somewhat different workflows. Subsalt, subbasalt, deep structures, conventional, unconventional, overpressure fields, etc. So that's becoming quite a complex and quite interesting challenges that we need to deal with. There's a lot of data management issues. So another important and interesting challenge, and perhaps also opportunity for some of the companies here, is to understand data management, because we need to deal with so many different data types. We have to deal with distributed data sets. In many companies, it's one team of people working from different countries on one data set. So you talk about 5 or 6, even 10 people working different element of the surveys, all integrated together, working in a true collaborative environment. This data that comes, real-time data that comes in from the field, real-time data that comes in from the geosteering process, from the well process, from the production information. There is this geological data that keep adding to the data. There are additional seismic data. So all that present a very interesting data management challenges as well as data security, because as you probably realize, the industry is very security conscious. So all those things are interesting areas where I think the companies here in Israel can contribute to. So far we mentioned geoscience. Unfortunately, or fortunately, depends on your point of view, it's not just one discipline. It's actually many disciplines. And if you sort of zoom in into a higher resolution, so to speak, of the process, you need to deal with geophysics. And now geophysics, you have processing geophysicists, interpreters, geologies, petrophysics, rock physics, reservoir engineers, drilling engineers, production engineers. All those disciplines are different disciplines where people are needed to be integrated to work together. You also look in the different domain, the way we like to sort of group those activities. Seismic processing and imaging, interpretation and modeling, reservoir characterization, reservoir engineering, well planning and drilling. I'll make a few comments on each one of them in the next few slides. Seismic processing and imaging, you've already seen some of those results. This is a seismic section. That particular one is a 2D section from a 3D seismic. I'm pointing out in circles just to show you what advanced imaging and advanced technology can do. You probably, if you see it at the slide labeled Institute Imaging, you can see the big difference that more precise and more fine-tuned imaging made to that particular section compared to the one labeled basic pre-stack depth migration. I mean, those are the type of things our industry is looking to do. Taking a very advanced science and use that science to create sharper images in the subsurface. See if I can get it work. No, Yep. Okay, there's also a quick movie here, which show you another advance in imaging, which is in situ imaging. And the ability is to use our science and convert the seismic experiment from being an experiment done at the surface level to the subsurface, and imagine that you're actually watching the seismic data from the point of view in the subsurface in the ground. And of course, by doing that, we're able to get a very high resolution, very detailed information of what we have there. The seismic interpretation modeling here, the challenge is, as I already mentioned before, is to go from regional scale, let's say the scale of the Levant Basin, into a specific, very fast into the high resolution prospect scale, from seismic scale to geological scale, seismic scale, as I mentioned already, tens of meters to geological scale, multi-surveys with a lot of information that we need to deal with. A typical survey of that kind could be 1 petabyte of data. So 1 petabyte of data that you need to deal with very fast, very quickly, at different scale, at different resolutions. Reservoir characterization and petrophysics. Again, what you do here, you delineate and characterize oil and gas reservoirs using all the disciplines, geology, geophysics, and petrophysics. Reservoir modeling engineering, you evaluate the reservoir once you find it, optimize the production, and create the model to do so. Basically, we're trying to show you how all those disciplines integrate together into what is sort of a full interpretation workflow. We'll try to make it work later, then we'll have a chance to present it again. So thank you so much.